Karunya will be presenting the flashcards on the topic electric field and electric charges in standard 12 physics. Carry on, Karunya.
So I started with electric field and electric charges. Now we'll be seeing topic 3.
Actually, this title itself is a very good presentation. Good. Because from the title, uh, you are going to introduce some concepts related to electric field and electric charges. So you have presented in a nice way.
So I started with topic 3. So the first will be seeing is Coulomb's law and its basic characteristics, electric charges, electric flux, applications of Gauss law, dipole, and electric field.
So you have done the topic 3 in a creative way. Good.
First, I started with electric field and electric charges. In that, we'll be seeing Coulomb's law, where C is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square, where 1 by 4 pi epsilon naught can be represented as K.
One
And
minute. What is this C? It should be F.
Coulomb's law. Sir.
It
Since
should
it's
be F.
okay, sir.
It is the force of interaction. So whenever you write any law or any, represent by equation, you do it with the diagram also. Okay. So when you say Coulomb's law, immediately you should be able to, that is, visualize the diagram. So this is Q1, this is Q2. So the distance between them is R. So based on that, you can explain. And you are talking about the force of interaction between these two charges. So the force of interaction between the two charges, it is a proportional to the product of the charges and inversely proportional to the square of the distance between them. So likewise, we have to proceed.
So that 1 by 4 pi epsilon naught can be represented as K and its value is 9 into 10 to the power 9 and its unit is Newton, where epsilon naught value is equal to 8.854 into 10 to the power
What you
minus
can do
12.
is that is a 1 by 4. You can write straight away. K is instead of putting like this. Some people just by looking at this flashcard, they may mistake that K is equal to 4 pi epsilon naught. That is not the fact. K is equal to 1 by 4 pi epsilon naught, right? So you can write it legibly here instead of marking like this. Okay, so K is equal to 1 by 4 pi epsilon naught. And its value is, what is
8.
that? No, no, no. K is equal to 9 into, and did you check the values correctly? I
Yes.
mean units, SI units. You please check simultaneously. Then what about this epsilon naught? And you can write what about the terms you are representing, I mean the symbols for which what are the exact terms. For example, Q1, Q2, the charges or the distance between them. At least you could have shown by the diagram also. Okay, then you can put up epsilon naught permittivity through free space. So likewise, you should have mentioned. So hereafter you can mention like this.
So
You
the
can correct
unit
it also later.
so the unit of epsilon naught is Coulomb square, Newton inverse and meter square inverse. Next we'll be seeing about force between multiple
No, it should be
charges.
called instead of calling square meter square inverse, you can put meter power minus 2. So Newton inverse you can say. Okay, but this cannot be called a meter inverse square. So instead you can put simply Coulomb square,
Newton.
Newton, either you can say Newton inverse or you can uh, plainly say Newton power minus 1, meter power minus 2.
Where F12 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 square into R12 cap.
Here also, that is, you must write what is F12.
It is the force between two particular charges.
Then what about F21? So how it should be called? So that is very important. Whether it is the force exerted by the first one because of second one, or it is because of the second one by the first one. So you have to explain very clearly. Okay. And why you Q1 Q2 divided by, and what do you mean by this R1 2 cap? What is
It's
that?
unit vector.
Unit vector. And you could have represented this by uh, as a vector also.
Uh,
Okay.
So now I have represented the electric field lines due to positive charge where Q is greater than 0 so that the electric field lines will exert in outwards.
Emerging outside.
Emerging outside. Electrical field lines due to a negative charge where Q is less than 0 so the electric
Merging at 1.
1. And then I have represented where the like charge repel each other and unlike charge attract each other.
You have to say like charges instead of pole, like charges.
Okay. And then we are going to see about the continuous charge distribution. It's just a simple formulas where sigma is represented as surface charge density, which is equal to del Q by del L, and rho is nothing but volume charge density, where del Q divided by del V, and lambda is represented as linear charge density, which is equal to del Q by del L. Now we'll be seeing about the Gauss law, which is phi is equal to q by 4 pi epsilon into r square into 4 pi r square since it is a spherical in shape. If we cancel out, we'll be getting q by epsilon naught.
So diagram is required here.
So I've done later.
Later. Okay. And what is this phi?
It is electric flux, sir. And then in a spherical sphere, the electrical field inside the field will be zero since there is no charge present inside the sphere. And electrical field outwards, the field can simply be represented as E is equal to 1 by 4 pi epsilon naught into Q by R.
Have you mentioned about the relationship between F and E?
No, sir. F is equal to QE is one of the formula.
F is equal to
QE.
EQ.
Hmm. And this is also the another representation where we'll be seeing this two formulas and applications of Gauss law, where E is equal to lambda divided by 2 pi epsilon naught R into n cap, and E is equal to sigma by 2 pi epsilon naught into n cap, which will be explained later.
Is there any explanation for the absence of R here?
Sir, this can be represented for that plane sheet, sir, Gauss law for a plane sheet.
This one?
So, sir, that one only for plane sheet,
What
and
about
that
this?
is infinitely long conductors. So, this one completed. Then we'll be seeing about conductors and insulators. Conductors where the substance through which the charge can flow easily, large number of free electrons are present. For example, metals, graphite, alkali, etc. And then we'll be seeing about insulators. Substance that does not allow the flow of charge, free electrons are absent. It's examples of glass, diamond, wood, etc. Now we'll be seeing about the basic properties of charges, where conservation of the first one is conservation of charges. The charges can neither be created nor destroyed, but it can be transferred from one form to another. Next, we'll be seeing about is quantization of charges, where its formula is Q is equal to Ne. It is defined as the total number of charges is equal to integral amount of electrons present in it. Where next is addition of charges. The charges can simply be added. Now we'll be seeing about the vectors form of Coulomb's law. In vectors form of Coulomb's law, when Q1, Q2 is greater than 0, both the charges can either be positive or negative. When Q1, Q2 is less than 0, when one charge is positive while the other is negative. As we said before, It can also be represented as F12 vector is equal to minus of F21 vector, which is Newton's third law. Now we'll be seeing about force between multiple charges. So in multiple charges, we can represent the force by vector form. So likewise, F12 vector is equal to.
So whenever you call this F12, F21, you should have the practice of calling it by a statement, by a definition, by an expression, suitable expression. For example, force experienced by one, that is exerted by two, second charge. Okay. So likewise, you should be able to use.
So F12 is equal, F12 vector is equal to K Q1 Q2 divided by R12 vector.
For example, why we represent like F12, F21? Because you cannot experience a force unless otherwise
an external force
an
is
external
applied.
agent acts on it. Okay, so when external agent, for example, Q1 that possesses a kind of force, but we don't experience it. You cannot get it. But when you take another charge nearer to them, there will be an force exerted by the second charge. Okay.
Likewise, F13 vector is equal to K Q1 Q3 divided by R13 the vector square into R13 cap. And then we represented it in n form where F1n vector is equal to Fq1 Qn divided by R1n vector square into R1n cap. So as a whole, it can be represented as F is equal to summation I is equal to 2 to n, where K Q1 Qn divided by 1i square vector into R1i cap. And
Actually, what do you mean by R cap when I say 1n? Can you express it?
sir, it is represented as
It is a
vector form divided by
of
modulus
divided by modulus of
vector.
1n. Okay.
Yes.
So this is nothing but the magnitude. Are you able to follow?
Yes, sir. So the note can be used here is the vector sum is obtained by using the parallelogram law of vector. And now we'll be seeing about the electric field, where the electric field is defined as the force experienced by a unit positive charge placed at one point where E vector can be represented as F vector divided by Q. So it can also be represented as E is equal to KQ by R square, which is expression of electric field. Now we'll be seeing about some basic properties of electric field lines. Electric field lines are continuous curves because they start from a positively charged body and end at negatively charged body, where you can see the simple representation of plus Q and minus Q. And then I have done a diagram based on electric dipole, which will be explained later. And now, no electric field lines exist inside the charged body. Thus, the electric field lines.
What do you mean by the electric field line? Which term expresses the electric field line?
Electric field lines, sir. E.
Flux, phi.
Phi. Oh, okay. Do not form continuous closed loops. No electric field lines of force can intersect each other because if they intersect at a point, we can draw two tangents, that is PA and PB, which is not possible. The electric field lines are always normal to the surface of the conductor.
Normal means what?
90 degrees, sir. Beta will be
Perpendicular.
90. Now we'll be seeing about the electric dipole. So this is the simple representation between plus q and minus q, where the charge will travel from minus to plus and the distance between them is 2d. That is two opposite charges separated by a distance of 2d. The formula
Separated by a small distance.
Yeah, okay, sir. Separated by a small distance of 2d, where the formula of it is P is equal to Q into 2A. It is also be explained as the product of magnitude of either charge and the distance between the two charge. So its unit will be coulomb meter and it is a vector quantity. Be seeing about the electric field due to an axial line where I have represented it through a diagram, and its formula will be 2 kp by r cube, where k is dielectric constant and p is dipole moment, where E is inversely proportional to r cube. So as the electric field increases, as the distance increases, the electric field intensity will be decreased.
What is P?
P is electric dipole, sir, where P
Expression.
Q into 2A.
What is A?
A is distance, that small distance.
Semi-length or semi-distance. 2A is the distance between the plus and minus charges. Now, when you say A, you have to say semi-length or semi-distance. Half the distance.
And now electric field due to an equatorial line where it is represented through a diagram where E equatorial is equal to minus Kp by R cube. And now we'll be seeing about the relation between E axial and E equatorial, where E axial is equal to minus twice of E equatorial. Then we'll be seeing about the torque due to electric field, where I have represented it through a diagram, and the where torque is equal to R cross F. When we remove the cross,
what is this straight line?
Sir, it is the electric field lines.
And why you are not marked with arrow mark? You should be like this, no?
Where torque is equal to R cross F, where we can represent it as RF sine theta. R is, as I said, it is 2A because it is the distance between the two charges. F is QE as we have taken the positive charge plus Q and sine theta, where 2A into Q can be expressed as P as we saw, where P is equal to Q into 2A and E comes as it is. So torque will be represented as P cross E, where the unit will be Newton. Now we'll be seeing about the conditions for the torque.
In fact, there is what is your inference from this? When you keep a dipole in an electric field, what happens?
Torque acts on it.
That is, torque means?
Twisting force.
Yeah, it will twist like this.
Now we'll be seeing about the condition for torque, where when both the theta and torque is zero, it will be a stable equilibrium. And when the theta is 90 degree, then the torque will be PE, which is maximum, and it is also an equilibrium.
Because theta is equal to 90 means sine 90,
1.
1.
When theta is equal to 180, then the torque will be 0. Since sine 180 is 0, then it will be unstable equilibrium.
These are the cases.
Yes, sir. Now I'll be explaining about electric flux. So phi will be equal to closed integral E dot ds. The number of electric field lines passing.
You have to say integral over the cycle.
Integral over the cycle.
Integral over the cycle of E into ds.
So
what is the ds?
Sir, the surface area of sphere.
Surface area element of the sphere.
Okay, sir.
Surface area element. That is ds.
So the number of electric field lines passing through the closed surface area element, which is represented as ds, it is a scalar quantity. Now we'll be seeing about the Gauss law. The total electric flux over the closed surface in a vacuum is 1 by epsilon times the total charge Q contained inside the sphere, where phi is equal to
actually, just by looking at this equation, you can define it. For example, phi is equal to, what is that? 1 by epsilon 0 times of the charge. That's it.
Okay. So when we remove the vector form, it will be EDS cos theta. So which is equal to Q by epsilon naught.
So it means that this is the dot product that results the scalar.
Okay, sir.
Usually vector product results a vector quantity, dot product results a scalar quantity. And that is why phi is scalar.
Okay, sir. Now we'll be seeing about the Gaussian surface, where the surface chosen to calculate the surface integral is called Gaussian surface. Now we'll be seeing about the proof for Gauss law, where phi is equal to closed cycle integral E dot ds, where E expression is kq by r square, where kq by r square is taken out. So since it is a sphere, we are writing it as surface area of sphere is 4 by r square. So if we cancel out, we'll be getting q by epsilon naught. Now we'll be seeing about the formula for application of Gauss law for an infinitely long charged body as I represented through a diagram, where E will be equal to lambda by 2 epsilon r, 2 pi epsilon r. And now we are going to see about Gauss law for a plane sheet, where I have represented it through a diagram, and its formula will be E is equal to sigma by 2 epsilon naught. And now application of Gauss law of a spherical shell or for a conducting sphere is we have three cases. The case one will be point P outside the shell. When there is a point P outside the shell, the formula can be expressed as, a second return. E is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. Where on case 2, we will be having the point on the sphere, so that E is equal to 1 by 4 pi epsilon naught into Q by, it is represented as capital R since we have to differentiate it. And now we'll be seeing about the case 3, which is the point will be inside the sphere. Since no charge is present inside the sphere, hence the Q will be 0. Since the Q is 0, electric field will also be 0. And now we have the chapter related formula, where the first one is Q is equal to NE, F is equal to QE, F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. It can also be represented as K Q1 Q2 by R square. Epsilon R is relative permittivity through free space is equal to epsilon M is permittivity through medium divided by epsilon naught is.
You can simply put the epsilon also. So
Okay.
epsilon r is equal to epsilon divided by epsilon. And that is why epsilon, that is a permittivity through certain medium, is equal to epsilon r into epsilon r.
Yes, sir. And then we have represented the formula for r cap, which is unit vector, is equal to r vector divided by modulus of its own vector. And then we have electric field formula where E is equal to F by Q. And the electric field expression is KQ by R square. As I said through derivation, E is equal to K summation I is equal to 1 to N into Qi divided by R In square. And then E is equal to 2 Kp by R cube as we saw in axial line. And in equatorial line, E is equal to minus Kp by R cube. And in torque.
That you can mention equatorial line, axial line.
And in torque, where torque is equal to P cross E.
Actually, this is a vector.
Okay, sir. And same as torque is equal to R vector into F vector. Then we saw about lambda, which is equal to del Q by del L, and rho is equal to del Q by del V, sigma is equal to del Q by del S, and E is equal to sigma by 2 pi epsilon R, and then
E is equal to lambda divided by
lambda divided by 2 pi epsilon R, and then phi is equal to Q by epsilon R, then E is equal to rho V divided by 4 pi epsilon R square, and then E is equal to sigma by 2 epsilon. Thank you.
Very good. So very clean presentation and neatly. I mean the layout is also very neat and it is not overcrowded with a lot of text. And I think this is one of the best presentations. Okay, very good. Keep it up.